squared y double prime plus alpha x y prime plus beta y equals 0. Where alpha and beta are constants. Okay. And what do you see about this? Well, where are its, what singular points does it have? What singular points does it have? When x is 0. Right? Okay? Because you're going to have alpha x over x squared, you're going to have beta over x squared. Right? And you see that when you multiply this first guy by x, the singularity vanishes. You multiply the second guy by x squared, the singularity vanishes. So you know that 0 is singular, but it's not that bad of a singularity. Right? It is a regular singularity. So 0 is a regular singular. And in the case of this equation, let's we can actually make a guess for what the solutions would look like. Emily?
Does it matter, like, when you multiply through, that we're left with the alpha and the beta? Like, are there something special or no?
Those are just numbers. So like any equation of this form with any numbers here are called the Euler equations.
So, okay.
I'm not maybe not
Never
wrong.
mind. It's just a wondering question.
You're wondering.
Like, will you always get the coefficients of those two?
When you do what?
Never mind.
Okay.
Go on.
Okay, sorry.
It has nothing to do with what you're saying.
Okay. Okay, sorry.
Well, I have a question. So when we have regular singular points, can we multiply through by those factors and then solve it like we would have before? Or something like that? I mean, if we're trying to find solutions.
What do you mean multiply through?
Like, just do what you did.
Multiply this by x and multiply this thing by x.
Yeah. And then we try.
No.
Okay.
No, very much no.
Very much
No.
no. Okay.
No.
That's just for a check.
Yeah, that's just to check how bad the singularity is, right? But you can't say, I'm just going to ignore this thing.
Yeah.
I'm going to multiply some of these guys by x's and just get rid of them. No.
I guess I wonder where that came from, but it's just to check it out.
Yeah, it's basically how bad is the singularity, right? But if you actually do that to the original equation, you've changed your equation.
Yeah,
Right?
definitely.
You've changed your equation, so that's not legal.
But we can find solutions even though it's not analytic at this point.
That's right. So it will turn out that things like this and things that are worse than this, but for which the singularity is regular, are we can find solutions. And so in this case, actually, they are very simple solutions. So for example, if you took, so in this case, in the case of Euler equations, the solutions are simple. You could make a guess, yx being x to the r. So you just take some power of x. And let me remind you, in case you've forgotten, that x to the r is defined to be e to the r ln x. So, if r is a irrational number, right? You're taking x to an irrational number. How do you define that? Well, you use the exponential function. In case you haven't seen it or you forgot. So it turns out the solution is simple. Things like this will work, and you just plug them in to figure out. You just plug them in, right? So plug it in. You get x squared r minus 1 x to the r minus 2 plus alpha x r x to the r minus 1 plus beta x to the r equals 0. And so that gives you r minus 1 plus alpha r plus beta times x to the r equals 0. Factoring out the x to the r. And so any x to the r where so y equals x to the r, where r is, by the quadratic equation again, of this form, will do. We'll solve the equation. Right, because you would want this thing to be 0. For this to be the 0 function, this coefficient has to be 0, and you solve for r. Here.
What does the negative 1 be with alpha?
Where does the negative 1 come from?
Or yeah.
Here, you see, you got r
Yes.
squared minus r, right? So you end up with alpha minus 1 times r.
Oh, okay, yeah.
Just do the bucket. Okay, and so right. So the point is that even though you have a regular singular point at 0, well, you can still get a solution. Okay, there's some trouble. So similar to what we did before. You get cases, like if the roots are distinct, if the roots are the same, or if the roots are complex. Okay, so if it's distinct, then it's easy, right? So case 1, the roots are, say, real and distinct, right? Then it's just x to the r1 and x to the r2 are solutions. That's the easy one. Case 2. Erase something that I need. 1 minus 1 plus alpha plus beta. Let's call this thing f of r. F of r. So case 2, the roots are double. You've got one double root, say. So f of r in that case is r minus r1 squared. in that case, of course, you have one solution. And how do you suppose we go about getting the second solution? Well, here, multiply that function and substitute back in. You could do that. So you could use reduction of order, right? So we could use reduction of order to get a second solution. But instead we'll do something completely different. Do we have time to do it? Let me think. No, we don't. We'll do it next time. So we'll do something a bit more clever than doing, I mean, reduction order is very clever